All right, today we're diving deep into something you probably never think about, but it's everywhere. Welding defects. We're talking about these tiny, invisible flaws that can have, well, massive consequences. Seriously, just think about it for a second. Your car, that bridge you cross every day, the building you're in right now, what's the one thing, this hidden force, that's holding it all together?
Yep, it's the weld.
That simple fused joint that takes separate chunks of metal and turns them into one solid, strong structure. It's fundamental to pretty much everything. But here's the kicker. What happens when that connection isn't so perfect?
Okay, so here's what we're going to cover. First, we'll look at the power of a good weld. Then, we'll get into the nitty-gritty of what a flaw actually is. After that, we'll check out the two main ways inspectors look for these problems, how they find the ones you can't see, and finally, wrap it all up with why getting this right is so important.
You know, it's so easy to just completely overlook this stuff. But we really do rely on the strength of millions, maybe billions of welds every single day. They're like this invisible skeleton holding up our entire world, our infrastructure, our cars, everything. And when it's done right, a weld is unbelievably strong. But that strength is only as good as its integrity.
So what happens when that integrity fails? What does that even look like? Well, that's where we get into welding defects. And a defect is basically any flaw that messes with that connection. We're not just talking about something that looks a little ugly. These are hidden dangers that can seriously weaken the whole structure.
Okay, first up is a really common one called porosity. So picture this, as the molten metal of the weld is cooling down and turning solid, tiny gas bubbles get stuck inside. It's like a flaw that's literally frozen in time, captured right at that moment of creation.
And a great way to think about this is like air bubbles trapped in an ice cube. You know how they make the ice weaker? It's the exact same idea here. Those little pockets of gas create weak spots right inside the metal.
All right, next up is something called slag inclusion. Now, this time it's not gas getting trapped, it's actual solid stuff. We're talking about impurities, like little bits of flux from the welding rod, or oxides that didn't get cleaned out properly. They just get stuck right inside the finished weld.
The perfect analogy for this, imagine you're baking a cake and you get little bits of eggshell in the batter. Nobody wants that, right? It ruins the whole thing. Well, in a weld, those little eggshells are a huge problem. They create a really serious weak spot.
So when you look at these other defects here, things like incomplete fusion, undercutting, overlapping, you start to see a pattern, right? A lot of this comes down to the welder's technique. If they move too fast, the metals might not fuse together properly. Move too slow and you get this messy overlap. It really is a fine art, a delicate balance between the welder's speed and the heat they're using.
But honestly, all those other defects, they've got nothing on the most dangerous one of all, a crack. See, the other flaws weaken a weld, but a crack, that's an active fracture. It's the one thing that keeps engineers and inspectors up at night.
And here's why it's so terrifying. A crack can cause a total failure, suddenly, with absolutely no warning. And this is a huge deal for parts that are under constant stress. We call that dynamic loading. Think about things that move or vibrate. You know, parts on bridges, cars, heavy machinery. A tiny, insignificant crack can just grow and grow under that stress until, bam, catastrophic failure. Okay, so we know these flaws are out there, and some of them are incredibly dangerous. So the big question is, how do we find them? Well, in the world of inspection, it really boils down to two main paths. You can either break the thing to test it, or you can test it without breaking it. Destructive testing is pretty much exactly what it sounds like. You take a sample of the weld, you put it in a machine, and you literally break it to see just how strong it is. Non-destructive testing, or NDT, is the flip side. It's this whole toolkit of clever ways to inspect the actual final product for flaws, but without damaging it at all. Not even a scratch. Now, obviously, you're not doing destructive tests on the final product, right? That would defeat the purpose. This is all done beforehand. It's how you qualify a specific welding procedure or test a welder's skill. You take a sample piece and you pull it, you bend it, you stress it until it breaks, all to prove that your materials and your methods are solid before you even touch the real thing. But when it comes to that actual finished part, say a girder for a bridge or a wing on an airplane, yeah, you can't exactly break it to check your work. And that is where the inspector's toolkit of non-destructive methods comes into play. Each tool is designed to find those hidden flaws without causing any damage.
And this really breaks down the strategy perfectly. If you're looking for a flaw on the surface, an inspector might just do a really close visual check, or use things like magnetic particles or special dyes that make tiny cracks pop.
But to find those really sneaky flaws, the porosity or slag that's buried deep inside the metal, you need to see through the metal. And for that, they bring out the heavy hitters, like X-rays or even ultrasonic sound waves.
Okay, let's pull all of this together. We've talked about the hidden dangers that can be lurking inside a bad weld, but also the really clever ways inspectors can find them. And the big takeaway here is how we bridge that gap, the gap between a hidden risk and guaranteed reliability.
When you think about it, there's this really powerful duality at play. On one hand, welding is this incredible force that literally builds our world. But on the other, it's not automatically perfect. There's always a risk of defects. So it's that super rigorous, methodical process of inspection that's what turns a potential weak link into the solid, safe, and strong connection that we all rely on every day.
And that kind of leaves us with one final big question. As we build bigger and more complex things, I'm talking taller skyscrapers, deeper underwater structures, the need for absolutely perfect welds is just going to get bigger. So the real challenge for the future is, how are we going to make sure that every single one of those connections is flawless every single time?